Okay, domain and range, part 2. So last part, it was all about determining them from a graph, so visual. Here we're going to be doing it more algebraically, functionally. To get start with, let's revisit some function families, because that's going to come in handy for determining domain and range. So as we look at this function here, and this one here, I want you to determine what is the function family and what is the parent equation. So I'm not asking you to come up with the equation for said function, just find the parent equation. Pause, give it a try. Okay, function family here, we would call this a higher polynomial, because it has more than one high-low point. And it would be something along the lines of y equals x to the power of n, where that n, remember, is always larger than 3. If it's 2, it's quadratic. If it's 1, it's linear. So n's got to be greater than 3. Here, this one, notice it starts at 0, 0, extends on forever. It looks to me to be a radical function, which we know is y equals the square root of x. This one probably is y equals negative square root of x because it's reflected. All right, so we're working with domain and range again. Let's revisit those definitions. So remember, domain we define as the set of all possible inputs. So these are our x values. The range we defined as the set of all possible outputs, so being the y values. So depending on the type of function, there are different things to consider with domain and range. So we're going to go through and kind of identify the ones that are sure, the ones that are always consistent, because there are a few that are pretty easy to find no matter what the function is, and then we're going to talk about those exceptions. So to get started, let's just revisit what's the parent equation for each of these. And then depending on the type of function, see if you can determine the domain and range for each of those types of function, if there's something that's always true, like if any are all real numbers all the time. Okay. So for linear functions, our parent equation is y equals x. So remember, that's just a function like this. This one, there are no limitations. The domain is always all real numbers, which we describe as r with an extra line through it, or you could write as x values from negative infinity to positive infinity, all acceptable answers. The range is the same, all real numbers, or again, another way to write it would be using ordered pairs. So all of these acceptable ways to write all real numbers. You can just pick one. Quadratic functions, remember? So those are our parabolas, or y equals x squared. The domain, so the x values, those are always going to be all reals. The range, remember with quadratics, does have a maximum or a minimum value. So the range depends on max or min. So for example, it'd be like y is greater than or equal to 4 or something, if the minimum's at 4. Trinomials. So these are y equals x to the third. These ones have all real number domain and all real number range. Higher polynomials, x to the n, where n is larger than 3. So these ones, you never really know. Sometimes they both have n behavior in the same direction. Sometimes they have opposite directions. So domain, though, that's always the same. There's never anything we can't plug in for x. Range, again, with higher polynomials, this one depends. You just have to check if there are maximum or minimum values. absolute value functions, remember, like this, have that like a Stark point. It's rigid, and those are y equals the absolute value of x. These ones, there's never anything you can't plug in for x, so our domain's all reals. For our range, again, it has a low point, so it depends on the maximum or the minimum if it were reflected, so facing down. Last one is exponential functions, so again, these look like this, or y equals a to the power of x, or b, some base to the power of x. For these, there's never anything you can't plug in for x. You can take something to the power of anything, so all x values work. However, with exponential functions, there's always a horizontal asymptote, so it always depends on the asymptote. Okay. So with these types of functions, it depends on like high or low points or an asymptote. So you'd want to kind of visually inspect those to determine domain and range. But the domain for all these is all real numbers. For the types of functions we're going to look at today, and you may have noticed there are some that weren't included in this table, these are ones that all have limitations on the domain, things you cannot plug in for x. So we're going to start with radicals, so root functions. And remember, with radicals, if you have a square root or really an even root in general, remember, you cannot take an even root or a square root of a negative. Remember, your square root must always be greater than or equal to 0. You can take the square root of 0. Can't take the square root of anything less than 0. So when I'm determining the domain, what we do is we check the inside of the root, and we make sure our domain will be all x values that make that square root greater than or equal to 0. So any x values that make this 0 or larger, that would be okay. Those would be considered our domain. Anything that's less than 0 would be outside of the domain. They're things you can't plug in because you can't take the square root of a negative. So what we do is we set the inside greater than or equal to 0, and then solve for x. So we add 19 to both sides, divide both sides by 2, and we get x is greater than or equal to 19 over 2, or 9.5. And this would be our domain. All x values greater than or equal to 19 over 2 would make the square root greater than or equal to 0, so that would be our domain. X is greater than or equal to 19 over 2. Or, again, we can express it as an order pair. So it'd be everything from 19 over 2 up to infinity. So either way would work in your expression of the domain. Finding the range is a little more challenging. It usually requires graphing, which we won't get into for today. Okay, so let's look at number 2. So we have y is equal to the square root of x squared plus x minus 6. So again, for finding the domain, you set what's under the root greater than or equal to 0. So in this case, we have a quadratic. So what we need to do is we factor into numbers, in this case, that multiply to -6 and add to +1. So those would be +3 and -2. We set each of those equal to 0. Solve for x, so we get x equals -3 and x equals 2. In this case, what's happening is there are, when we're factoring, there's some division happening. And when you divide with inequalities, remember the sign flips, so some weird things tend to happen when we're doing this. So remember, we do have this inequality where it would be greater than or equal to. But whenever you have more than one value, essentially what you have to do is you have to check using a number line to determine your actual domain, because things get a little funky with these values here. So what we need to do is we consider these two values that we came up with, -3 and 2. And what we're going to do is we're going to check values to the left, to the middle, and to the right of -3 and 2 to see what gives us a positive value and what gives us a negative value. So if we choose a value, say -3, what we will do then is we want to plug that into the original equation, so we'll plug -3 in. So I'll put my work down here. So if we plug in -3 for x, let's check to see if that is actually greater than or equal to 0. So -3 squared is 9, -3 minus 6, or sorry, we don't want to use -3. You want to pick someone to the left of -3 because we determined that's when it's 0. So let's choose -4, my bad. So -4 squared would give me 16, -4 minus 6. 16 minus 4 is 12, minus 6 is 6. 6 is greater than 0. So whenever I pick values to the left of -3 or less than -3, we'll get something positive. Let's pick something in between. So let's try 0. So if I plug in 0 for x, I'll get 0 plus 0 minus 6. -6 is not greater than or equal to 0, so we get a negative value there. So that means if I plug in 0, I'm going to get a negative root, which you can't have. Let's pick a number to the left, to the right of 2, so let's pick like +3. So we'll have 3 squared plus 3 minus 6. So 9 plus 3 minus 6, is that greater than or equal to 0? 9 plus 3 is 12, minus 6 is 6, and yes, 6 is greater than or equal to 0. So what I've determined is that any values less than or equal to -3 and greater than or equal to 2 will give me a positive under the square root, meaning those are the values in my domain. So the way I would express my domain is it would be all x values less than or equal to -3, as well as all x values greater than or equal to 2. So when we're working with these quadratics, it has to do with, if you remember, like when you multiply or divide by a negative, you have to flip the sign. It's kind of that same idea. You just have to check because sometimes the signs flip in certain cases. Okay. So we'll do another one. You can probably see it's a quadratic, so the same type of idea is going to apply. So we'll have y equals, we want to check, figure out what values of x will make this greater than or equal to 0. That'll give us our domain. So we factor. This will factor into numbers that multiply to 20 and add to 12, which in this case would be 10 and 2. And then we solve for x. Set each equal to 0 and solve for x. So we get x equals -2 and x equals -10. So we can set up a number line and look for what values will I get positive or negative when I plug in numbers less than -10, between -10 and -2, and then greater than -2. So if we start over here, you can start with like -11, for example. So I'll do my work down here again. So let's plug in -11 for x. See, is that greater than or equal to 0? Well, -11 squared is 121. 12 times -11 would be -132. And then we have plus 20. 121 minus 132 is -11. Plus 20 is 9. So we get 9. Yes, that's greater than or equal to 0. So when I choose values less than 10, I'm going to get positive. We can pick a number between now. So I'm going to keep things low. So I'll try -3. So let's plug in -3 for x. Check, is that greater than or equal to 0? -3 squared is 9. 12 times -3 is -36 plus 20. Can already see that's going to give me a negative value, so no. And then lastly, you try a value to the right. So if you can ever pick 0, that's always nice. So 0 is to the right of -2, so when I plug in 0, I get 0. plus 12 times 0, which is 0. So 0 plus 20, yes, that's greater than or equal to 0, so it's positive. So our domain would be all x values then less than or equal to negative 10, and all x values greater than or equal to negative 2. It has to be or equal to because we've determined that when we plug in negative 2 or negative 10 for x, we'll get exactly 0. You just need to figure out the other sides. Okay. All right. You've got a few more problems here. Why don't you just take the first two here, give those a try on your own, pause the video, and then check back in, see if you got them. Okay. For number 4, again, set the bottom equal to, set what's under the root equal to 0, solve for x, so we get x is greater than or equal to 2. No x squared involved, so you don't have to be checking or anything like that. It's only when you get more than one value. Next, set what's on the inside, greater than or equal to 0, factor. So we get positive 3 and negative 3 for our factors, which means our roots would be negative 3 and positive 1. So set up our number line here. So we're looking for values around those. So anything to the left of negative 3, so we'll try plugging in, let's say, negative 4. Check, is that greater than or equal to 0? So we get 16 minus 8 is 8, minus 3 is 5, so we get 5 is greater than or equal to 0, yes. Pick a number in between, so we can try 0 here. So 0 plus 0 minus 3 is not less than, greater than or equal to 0, it's less than, so it's negative. Then pick 1 to the right, so if we pick 2, 4 plus 4 is 8, minus 3 is 5, so yes. So we've determined our domain would be everything less than or equal to negative 3 and greater than or equal to 1. Okay. All right, that, in my opinion, is the most challenging. It gets a little easier from here. Okay. All right, let's look at rational functions. So with rational functions, remember, you cannot divide by 0 because it's undefined. So what we're doing when we're determining the domain, all possible x values, our domain for rational functions is generally speaking just going to be all possible x values except whenever the denominator is equal to 0. So what we do is we set the denominator equal to 0, and whatever values we get, those are the values that are not in the domain. So we solve for k here. So we can factor a k from both. We have two factors, so we set each factor not equal to 0 and solve for k. So we get k cannot equal 0. And then over here we subtract 9 from both sides, divide by 7. So we get k is not equal to negative 9/7, as well as k cannot equal 0. And the assumption here is that all real numbers, or all values of k work except for 0 and negative 9/7. Because when you plug those in, you get 0 in the denominator. You can have 0 in the numerator, that's fine, just not in the denominator because it's undefined. So with rational functions, you're just looking for what values in the denominator make my function 0. Okay. Number 2. This one's a little interesting. So we have x minus 2 over x minus 2 times x plus 1. So your inclination is probably going to be, oh, I see x minus 2, let's cancel. When you are graphing this, that could be valuable. However, you have to work with the function the way that it's given to you when you're determining domain and range. So we do want to make sure to set that whole thing equal to 0 and factor it. It's already factored for us. And solve for x. So we'll get x cannot equal 2 and x cannot equal negative 1. When you're graphing, it will be helpful to cancel, but in this case, no. You still just set the denominator not equal to 0. Okay. All right. Let's do this. Why don't you try these two on your own? Pause the video, give them a try, determine the domain. Pause. Okay, we're back. So way to determine the domain, set the denominator not equal to 0, solve for x. So we get x cannot be -2. Over here, set the denominator not equal to 0. Solve for m in this case. So let's factor. So we have -8 and -1. So m cannot equal 8 and m cannot equal 1. Okay, so that's rationals. So far we've done radicals, so root functions, where you can't take the square root of a negative, so it must be greater than or equal to 0. Next we did rationals, where you can't divide by 0, so it must be not equal to 0. Set the denominator not equal to 0. The last one we're doing here is logarithms. So logarithms, maybe not super familiar, but you may recall you cannot take the log of negatives or 0. Can't take a log of a negative number or 0. So in this case, if it can't be negative and can't be 0, you have to look for greater than 0. So not greater than or equal to, just greater than 0. So this one's a lot like radicals in that now we just take what's on the inside of the log, and to find our domain, you would take what's on the inside and you'd set it greater than 0. So whenever this is greater than 0, that's when the x values are in our domain. So we can add 4 to both sides, divide by 3, we get x is greater than 4/3. So whenever x is greater than 4/3, we have values in our domain. Okay. We have a natural log now, an ln. So ln, remember, same thing as a log base e. So you treat things the same. Just because it has an ln, just because the log base is different, doesn't mean you have to do things differently. You still just take the inside, set it greater than 0, which you'll notice we've got the exact same thing. So you get x is greater than 4/3. Okay, number 3, we have log base 4. So now again, different base, that's okay. It doesn't matter. The base doesn't matter when you're thinking domain. It will change the way your function looks, but you still just set the inside greater than 0 and solve for x. So in this case, we'll subtract 10 from both sides. Now we multiply both sides by -5/2. And in this case, we're multiplying by a negative, so that sign flips. And -10 times -5 is 50. 50 divided by 2 is 25. So we get x is less than 25. Okay. All right, why don't you take a moment, pause the video, and try these two. Pause. Okay, so here, 1/6 minus 8, set greater than 0. Add 8 to both sides. We get x, then multiply by 6. We get x is greater than 48. Number 2, set it greater than 0. Add 12 to both sides. Oops. Multiply by 3, we get x is greater than 36. I should mention, if like this had a +4 or something like that, you don't do anything differently. You still just look on the inside of the log and set it greater than 0. Okay. All right, so that covers what we're doing today. So 3 types of functions with special domains. Logarithms, can't take the log of negative or 0, so you set it greater than 0. We have rationals, which can't be divided by 0, so you have to set it not equal to 0. And then we have radicals, which you cannot take the square root of a negative number, so you set the inside greater than or equal to 0.